students, I am Dr. Rajesh Panja, Assistant Professor, Department of Physics, Techno India University. As you know that we have started a lecture series which is based on your experimental physics, and you all know that experiment is a very important part for your engineering as well as for any scientific subject. So, what is the purpose of this lecture series? We want to provide you the proper way how to perform the experiment in your laboratory to get the knowledge, or in other words we can say to get the complete knowledge about the subject. So, today we have planned to discuss very important experiment which is the determination of Young's modulus of a material and which is in the form of the beam. As you know that beam is like that one, and what is the condition for the beam? Beam is a condition the length much more greater compared to its breadth compared to its depth. This is the condition for any beam. So, we would like to find out the Young modulus for that beam. We have splitted this whole experiment in three parts. First, we will discuss very quick and very short lecture on the theoretical part. Second, we will directly move to the experimental procedure where we will demonstrate how to perform this experiment clearly and precisely. In the third part, we will discuss about the calculations, error calculation, precautions and discussion in the third part. So, let us start the first one. As you know that the Young modulus, which is the elastic, related to the elastic property of the material. If you take iron bar, steel or any other materials, its Young modulus is different, and I believe that you have already studied this one in your school days. So, as it is the material property, it does not change with any other parameters. Here we will find out this Young modulus for a beam with the method of flexure. What is the Young modulus? As you know that Young modulus is defined as stress by strain. For a moment consider it is a material, maybe it is a wire of iron or steel whose cross section area is A, and let us say its length is capital L. Now, if we apply a force F along this direction and consider due to this force there is an elongation of small l, then as we know what is the strain? Strain is small l by capital L. And what is the stress? How much force is created per unit area? This is the stress, that is F by A. So, this is the definition of Young modulus. But here what we will do? But in our experiment what we will do? We will not use directly this relation, and we have modified this formula which is known as the Flexor method, and according to this method, and which is beyond the scope of this discussion from where we have got this equation, but you have to know this formula to determine the Young modulus of the material by the Flexor method. What is the formula? It is G LQ by 4BDQ small m by capital M. What is the G? G is nothing but the acceleration due to, and G is the acceleration due to gravity. What is the L? L is nothing but the effective length of the beam. What do you mean by the effective length? Actually, during this experiment you will observe that the beam is placed over two sharp edges, knife edges, okay, and the distance between these sharp knife edges is actually the effective length of the beam. And how do you measure that one? You have to use this meter scale, and you will get it may be 90 centimeter, it may be 80 centimeter, you will get this L. Now, what is the B? V is the breadth or width of this bar. How to measure that one? For that you have to use this slide calipers. I think that you all know how to use this slide calipers. If you forget, just visit our previous video where we have demonstrated how to use this slide calipers. Okay. So, using this slide calipers we can measure this breadth of this beam. Next, what is D? D is nothing but the depth of this beam, that much, the thickness of this beam. How to measure that one precisely? We will use this screw gauge, right? Okay. And you have to much more care about this D term, because it is the depth and there is a cube term. So error may come highly from this D term. So you must have to be careful when you are measuring the depth of this beam using the screw gauge. Now, what is this M and what is this L? So for that moment, I would like to request you, please go through little bit about this experimental part. What we will do? Actually, this beam is placed, as we have stated, in between these two knife edges, and there one load is placed through this hanger, and this hanger is placed at the middle of this effective length. So when you just place this load, it is almost 500 gram, there will be a microscopical depression, bending of this beam. So how to measure this bending? For that you have to use the travelling microscope. We have already demonstrated how to measure or how to use the travelling microscope in our previous lecture. And this depression is denoted by small l. So what will happen if we increase load much more? If you increasing the load, the depression will also increasing. So there will be a relation between load and the depression. And ultimately, for different loads, if you plot a curve, I think it is clearly, you can observe that one. So along this x direction, if you just vary the load from 500 gram, 1000 gram and so on, and using the travelling microscope, if you find out how much depressions are there, you will get a straight line, and from that slope you will get this M by L ratio. So directly from that curve you will get this whole term M by L, and you have already measured this capital L, this B, that is the breadth, and D, that is the depth of the beam. So you know about this constant term, and from the curve you will find this M by L ratio. So you will directly get this Young modulus. So in next we will directly move to the second part, where we will demonstrate the whole experiment. So let's move that one. So this is the experimental setup for Young modulus determination of a material. As you can see that the beam or the bar is placed over two stand, and there is two sharp knife edges. And what is the effective length right now for this bar? The distance between these two sharp edges is the effective length. And you can clearly observe at the middle there is a frame, and at the bottom of this frame there is a hook, and through the hook there is a holder for load. So what is the purpose of this load holder? So we can place easily any load here, and if I place any load at this hanger, there will be a depression within this bar. So now what is the working principle? As we have discussed previously, I would like to remind one again. So let's move to the working principle, then we will back again what is the measuring steps. So you can see clearly that the Young modulus y is equal to g L cube by 4v d cube. So L is the effective length, B is the breadth of the bar, and D is the depth of the bar. M by L, L is the depression due to the load, and first we will measure this M by L ratio. That means for different loads how much depressions will be there, we will record that data. So let's move to the travelling microscope, and how to measure this microscopic depression, we will learn that one clearly. So initially you can see that there is no load, so that means there is no depression or bending of that beam. So right now first we would like to focus the tip of this frame using this travelling microscope, and before that I would like to show you what is the present situation or present picture of this tip through the microscope. So right now you can see that the tip is inverted through the microscope and it is little bit blur and it is not also coincide with the cross point. So first of all we have to make this tip clear. That means we have to do the focus of our microscope and we have to make this tip end coincide with the cross mark. Let's do it, and what is the process to do we will show you clearly. So first we will focus the tip using this screw. So if I rotate this screw accordingly, so then this tip will be very clear through this microscope. So now I am focusing the tip and it is now clear, and I will show you later the picture of present condition. And here also I would like to make the tip coincide with the cross point, and for that we have to move this travelling microscope little bit right side, and I will use this screw to move the travelling microscope. We have already made separate video, the working of travelling microscope and how to use the travelling microscope. So I would like to suggest you go through that video first and then move here. So I am now moving the microscope to make the tip coincide with the cross point, and now it is clear. So I will show you the present picture after focusing and making the coincidence of the tip with the cross bar. Now you can see clearly that our frame tip is clear and it is also coincident with the cross point, and this is the condition when there is no load. Now at that time we have to take the tip height. Where is my tip right now? And for that I will use this scale which is graded over the microscope. There is the two scales, one is the main scale and another one is the Vernier scale, and using these two scale, first of all we will take the initial reading without load, and then after placing several loads we will again measure this displacement. So how to take the reading? Let's do it first. You can see there are two scales, one is the main scale and another one is the Vernier scale. So first of all, after focusing you have to take that data where the 0 of the Vernier coincident with the main scale reading, and here it is clear. You can see that it is 0.10 and it is 10.1, 10.2, 10.3 and 10.4. So at the 10.4 the 0 reading of the Vernier scale is coincident with the main scale reading. So our main scale reading will be 10.4, and after that to find out the Vernier readings we have to check very carefully that which gradation of Vernier is exactly matched with the linear scale, and that reading will be your Vernier reading. And before taking the Vernier reading I would like to show you the table which you have to make before taking the data. So this is the load depression record by travelling microscope. First of all you have to calculate the Vernier constant of the travelling microscope, which we have already calculated, which is 0.001 centimeter, and it is the number of observation. First load in kg, so initially we do not have any load, so we can make it as the 0, and we have to take the readings when the load is increasing. So the main scale reading in centimeter, as we have seen the main scale reading is 10.4. Now we have to check what is the Vernier. Then if I get the Vernier, then we will find the total reading, that is R1 is equal to main scale reading plus Vernier reading into Vernier's constant. Then we can get one data when there is no load. Similarly we will go for different loads. First of all we will use the 500 gram or 0.5 kg. Again we will measure the main scale reading, vernier reading, and we will find the total. So in this way we will use the 1 kg, 1.5 and so on. Similarly in this table we will just releasing one loads and another, and decreasing the loads we will take the same data, and after that we will take the mean of these two data, and finally we will get the displacement depression in centimeter. So don't worry for that, we will show you the complete calculations also. First try to learn how to measure this vernier reading and find out the diffraction. So let's move to the travelling microscope once again to get the vernier reading. So to find out the most suitable vernier reading, you have to check very carefully that which mark is coincident with the main scale reading, and you can find it may be different for different persons, but there should not be so much difference, but you will find that this is 0, this is 10, 20, and if we move that is 30, 31, 32. In my opinion 32 is the proper reading for that case, so we can take the vernier reading is 32. So now I will put that data in the table. So what we have found out, the vernier reading is 32. So what is the total reading now? So total reading R1 is equal to S means 10.4 plus vernier reading is 32 and vernier constant is 0.01, and you will get the result in centimeter. Similarly we will move for 0.5 kg load and try to measure the diffraction. So let's move to the experimental setup. Okay, now very carefully I am placing the load, this is 500 gram, in that hanger. So what will happen? Will the tip should be in the same position, or there will be a displacement of the tip? Obviously there will be a displacement of the tip, and let's see after placing the load what is the picture through this microscope. So here it is clear that now our tip is not coincident with the cross mark, but it is in the focused condition. That means there is a diffraction or bending of the bar. So what we have to do right now, we have to make this tip coincident with the cross mark by moving the travelling microscope, and which I am going to show you right now. So we have seen the tip is little bit upward direction. Why it is so? Because there is an inversion through this microscope. So we have to move this microscope in the downward direction to make the tip matched with the crossbar. So let's do it. So I am moving very slowly using this screw, and right now it is well matched with the cross mark, and I will show you that one also. So you can see after moving the travelling microscope in the downward direction, the tip of the frame is matched with the cross mark. So let's check how much depression is there after placing the load, and how to find out that one. Now we will check this microscopic reading, that means the main scale reading and the vernier reading. So let's check the main scale reading first. Okay, so now you can find where is the 0 of the vernier is matched with the main scale. So this is 10, this is 10.1, this is 10.2, and I think this is 0.5. So this is 10.25. Okay, so now let's take that data, and you can also simultaneously measure the vernier, most matched vernier reading. So let's focus it. Okay, so I think it is about 20, it is 30 in the upward, it is 40, 41, 42, 44, 45. So according to me this result vernier reading is 45, and the main scale reading is 10.1, 10.2 and 10.25. So let's take that data. So here it is 10.25 because the smallest division is 0.5 is there, and the vernier reading is 45, and you can get another R1 is here. So, similarly now I will place the load 1 kg, 1.5 and so on, and we will get the same result, right. And in that table you have to repeat, after placing all the loads you have to remove loads one by one and you have to take this data accordingly. And at the last you will take the mean. Mean means there you will get one R1, here also you will get R2. So, mean is R1 plus R2 by 2 in centimeter. So, this is for the 0 load reading. Let us say this is A, and after placing any load you will get another reading, let us say this is B. So, what is the difference now? So, L is equal to B minus A, and after fulfilling all this data I will show you later on. So, that is all. You have learned how to measure the bending of the beam by travelling microscope. Later on, the third part we will discuss the full calculation and how to do the graph, and there I will discuss about the precautions and discussion. Okay, let us move to the part 3.